So for our example here, we're going to return to the GDP data to find the equation of the regression line for the gross domestic product and CO2 emission data as before. Now, in this case, what we're going to start with is finding the pieces that we need. And I'll say that generally, when we're working through this, there are nice things in the calculator, just like before, for being able to find all of these pieces and actually, well, not necessarily find all the pieces, but get to the final answer. But I'm going to go through parts of the steps here, just so you have them for reference. Now, if we want to do this by hand, we'd start by finding those sums x and y, which if we were doing other things by hand, we already had, but whatever. First, we need to get the sum over the x values, which in this case would be 22.9. Remember, that's $22.9 trillion. Then we can do something similar, get the sum over the y values, and for that we would get 5,129.7, where that's 5,129.7 million metric tons, so about 5 billion metric tons of CO2. That's quite a lot. Then we do the more involved work with the sum of products, sum x, y, and for that we will end up getting 14,350.74, and it doesn't really have units in this case. And then finally we need the sum over x squared, so we need to find that piece, that piece, that piece, that piece to get m. We're going to end up with here 65.49. Now with these four pieces, we're going to plug them into that formula for the slope. And it's not a very nice computation, but at the very least it's just four numbers with some multiplication in there. You've done harder work than that if you were going to do it by hand. Still would recommend you do it by hand anyway. For the slope m, or if you see it in the calculator a or b, you're going to end up with a value that is approximately 199.6346. So what this says is, based on our model, you would expect that for every additional $1 trillion in GDP, a country would release about 200 million metric tons of CO2. Emit. Be more specific about it. Meanwhile, if we want to get the value for b, the intercept, we just need sum over y divided by n. So this value, which is going to be divided by 10 in this case, minus the value m times this one, also over 10. I'm not going to write out the steps here, even though it's a little bit simpler than that last problem was. But you will get that b, in this case, is about 56.036. And what this value b represents is the CO2 emissions for a country with no GDP, which represents an obvious limitation of the model, because a country with no GDP, you wouldn't expect to be emitting very much, because a country with no GDP doesn't exist. So, again, with these types of scenarios, we're taking a bit of creative license with reality when it comes to making these things, and we have to understand that, as we'll see with applications and how we can use this stuff, we do have to be careful, because obviously, in some cases, the value that we're getting doesn't actually have real-world meaning, or the real-world meaning it has is probably not useful. Anyway, that's what our two pieces here look like. So if you wanted to put them together, you would get that the linear regression equation here, up to my ability to write the letter y, will have approximately the form 199.535x plus 56.036, up to my ability to read and write. And as a result, if you want to think about what this looks like on a scatter plot, what the regression line looks like on a scatter plot, you'd have a picture of something like this, where you can see on there how that intercept hits the y-axis, what that actually looks like at that 56, and then how this thing tracks off further along in terms of x and y values, and also get a sense of what those residuals look like. That in terms of this scatter plot, a couple of the points are pretty close, a couple have a pretty decent gap, but for the most part, the pattern does fit decently well. In particular, if we were to let x equal 2.4, if we plugged 2.4 into that equation there, we would get a y value, in this case a y hat value, of approximately 534.92, which would have a residual of about negative 9.08. That is to say, the prediction would be 9.08 million metric tons below the actual value at 2.4. Now, I will say that when it comes to these computations, you can do this by hand. Now, these are not the prettiest symbols you've ever seen, but they're not the worst computations you've ever done. That said, in the calculator, there are a few different things you can use with the linear regression menus, whichever you're most comfortable with. Me personally, I like the linear regression t-test for reasons that we'll see when we get on to section 9.3. But whatever you use, as long as you're able to get the pieces M and B and can see what that picture looks like, that's the most important part when it comes to getting these values. Whether or not you have the sums, not so relevant to me. Anyway, now that we've seen a little bit of how you can make one of these guys, you can make a regression line and then look at what the residual might come out as from the regression line. Next thing we're going to do is see a bit more on how you can apply this information to make predictions.